3,000 years ago, in the middle of a desert where summer temperatures routinely exceeded 115 degrees Fahrenheit, Persian engineers built towers that pulled cool air into buildings without a single moving part. No compressor, no refrigerant, no electricity, no maintenance schedule, just clay, wind, and geometry. Those towers are still standing, 700 of them, in one city alone. The city is Yazd, Iran. The towers are called Badgir, windcatchers. The tallest one rises 110 feet and has been cooling the same building since 1747. 279 years, 0 kilowatt hours. By the end of this video, you will understand why an Egyptian architect was nearly erased from history for trying to bring this technology to the poor, and why the International Mechanical Code was quietly rewritten to make this type of cooling effectively illegal in every new American home. UNESCO designated Yazd a World Heritage Site in 2017. They described it as a living testimony to intelligent use of limited available resources in the desert for survival. The Dawlatabad Garden, where that tallest tower stands, was built by the governor Mohammad Taghi Khan Bafki during the Afsharid dynasty. It has never been plugged in. It has never been serviced by an HVAC technician. And it is not a museum piece. People still use it. The physics is not complicated. That is part of the problem. A Badgir is a vertical shaft, typically divided into 4 internal quadrants that rises above the roofline of a building. Whichever direction the wind blows, at least one quadrant faces into it. Wind enters the windward quadrant under positive pressure and is channeled downward into the living space below. Simultaneously, stale, warm air inside the building rises through the leeward quadrants and exits through the top of the tower under negative pressure. The system creates continuous cross-ventilation with 0 energy input. The wind does all the work, but the Persians did not stop at 4-sided towers. They built 2-sided towers, 6-sided towers, and 8-sided towers, depending on local wind patterns. In coastal regions where wind blows primarily from one direction, they built single-sided Malkaf-style catchers, oriented permanently toward the prevailing breeze. In desert cities like Yazd, where wind shifts direction seasonally, they built the 4- and 8-sided versions to capture air from any angle. The construction materials varied by region and era: adobe and mud brick in the earliest versions, fired brick with lime mortar in later Persian designs. Some towers incorporated internal baffles made of woven reeds to filter dust and sand from incoming air before it reached the living space. Others included cisterns at the base where incoming air passed over stored water, combining ventilation with evaporative cooling in a single integrated system. The Shesh Bajiri Ab Anbar in Yazd, one of the most famous water reservoirs in Iran, uses 6 windcatcher towers working in concert to keep a massive underground water cistern cool enough to preserve drinking water through the entire summer. 6 towers, 1 reservoir, 0 electricity. It has been working for centuries, but here is where it gets elegant. In Yazd, where summer air temperatures exceed 110 degrees Fahrenheit, the Persians did not just ventilate, they cooled. They routed the incoming air over shallow pools of water or through underground channels called qanats before it entered the living space. The evaporative effect dropped the air temperature by 15 to 25 degrees Fahrenheit. A computational fluid dynamics study published in the journal Renewable and Sustainable Energy Reviews found that windcatchers combined with evaporative cooling systems reduced indoor cooling loads by 73%. Another study found that wind speeds as low as 5.5 miles per hour could provide thermal comfort across 50 to 80% of the ventilated space. A separate research program measured temperature reductions of up to 21.6 degrees Fahrenheit, depending on tower configuration and ambient conditions. That is not theoretical. That is measured. In peer-reviewed literature, using computational fluid dynamics validated against wind tunnel experiments. And it is not just ancient history. In 2000, the United States National Park Service opened a visitor center at Zion National Park in Utah. The architects incorporated cool towers, modern adaptations of the Persian Badgir principle, using evaporative pads at the top of tall shafts to draw hot desert air through wet media and deliver cooled air to the interior below. The National Renewable Energy Laboratory evaluated the building and found it used 70% less energy than a comparable federal building constructed to the Federal Energy Code, 70%. The cooling system required no compressor, no refrigerant, no ductwork. The building did not cost more to construct than a conventional facility. It has been operating for 26 years, I had to read that number twice. 26 years of passive cooling in the Utah desert. The Zion Cool Towers stand approximately 32 feet tall. Hot ambient air enters through louvers at the top, passes through wetted cellulose pads, and the cooled air, now heavier than the surrounding warm air, drops naturally through the shaft and flows out at floor level. On a day when the outdoor temperature reached 106 degrees Fahrenheit, the cool tower discharge air measured 68 degrees Fahrenheit, a 38-degree temperature drop. No compressor, no electricity, just water, gravity, and evaporation. The total energy cost for cooling the 7,600 square foot building came to roughly 43 cents per square foot per year. A comparable mechanically cooled building in the same climate zone would cost between $3 and $5 per square foot per year for cooling alone. And this building is not a secret. It is a federally funded visitor center that millions of tourists walk through every year. The National Renewable Energy Laboratory published the performance data in a technical report numbered NREL/TP-550-34607. It is publicly available. Anyone can read it. But here is what should keep you up at night. In the United Kingdom, a company called Monodrat has been manufacturing and installing commercial windcatcher systems for decades. Their windcatcher classic product divides a rooftop unit into 4 quadrants, exactly like a Persian Badgir, and provides natural ventilation to schools, offices, and commercial buildings. These systems comply with Part F and Part L 2A of the UK building regulations. They require no electricity. They have no moving parts. They are installed in hundreds of buildings across Britain and Europe. They are legal. They are code compliant. They work. In 2014, a team of researchers filed an international patent application, PCT/GB/2014/052263, for an advanced windcatcher design incorporating heat pipe technology that achieved even greater temperature reductions. The research, conducted in collaboration with UK universities, used computational fluid dynamics, modeling validated against physical wind tunnel tests, to optimize the arrangement of heat pipes within the natural ventilation airstream. The optimum configuration achieved maximum heat transfer at a streamwise distance to pipe diameter ratio of 1.0. The technology was developed specifically for modern buildings in temperate climates where traditional evaporative methods are less effective. The point is not that one design is better than another. The point is that this technology is being actively developed, patented, researched, installed, and regulated in the United Kingdom. It is a living, evolving engineering discipline with peer-reviewed literature and commercial products and building code compliance pathways. Now cross the Atlantic. The International Mechanical Code, which governs mechanical systems in most American jurisdictions, contains a provision that has been quietly tightened over the last 2 decades. Section 4.03 requires mechanical ventilation for all Group R occupancies, which includes every residential dwelling in the country. The International Energy Conservation Code works in tandem with the International Mechanical Code to mandate whole house mechanical ventilation in accordance with Section M 1505.4 of the International Residential Code. The City of Philadelphia issued a formal frequently asked questions document clarifying that natural ventilation is not permitted to meet outside air requirements for residential buildings under the International Mechanical Code. Not insufficient, not supplementary, not permitted. Let me say that again. A technology that has been cooling buildings in 115-degree heat for 3,000 years. A technology that the National Renewable Energy Laboratory has documented working at 70% energy savings in a federal building for over 2 decades. A technology that is legal and code compliant in the United Kingdom right now. That technology is not recognized by a single section of the International Residential Code as a valid cooling strategy for an American home. 0 sections. I checked. The American Society of Heating, Refrigerating, and Air Conditioning Engineers publishes Standard 62.2 for residential ventilation. It requires mechanical ventilation. ASHRAE. Standard 55 governs thermal comfort. It does not include passive windcatcher ventilation as a recognized cooling strategy. There is no pathway. There is no alternative compliance route. There is no performance-based exception that would allow a homeowner to install a windcatcher and demonstrate that it meets comfort and air quality standards through measured performance. The code does not say windcatchers are inadequate. The code does not mention them at all. They simply do not exist in the regulatory framework. And here is the part that should really bother you. The air conditioning equipment segment of the global heating, ventilation, and air conditioning market generated $130.7 billion in revenue in 2024. The total global HVAC market was valued at $299.28 billion that same year. In the United States alone, air conditioning accounts for 19% of all residential electricity consumption. That is 254 billion kilowatt hours per year, according to the United States Energy Information Administration. Every one of those kilowatt hours generates revenue for utility companies. Every air conditioning unit sold generates revenue for manufacturers. Every service call generates revenue for HVAC contractors. Every refrigerant charge generates revenue for chemical companies. The average American household spends between $200 and $300 per year on electricity for air conditioning alone. Multiply that by 131 million households, and you begin to understand the scale of the revenue stream that passive cooling threatens. That is roughly $30 billion in residential cooling electricity costs flowing to utility companies every single year. A wind tower intercepts that revenue at the source. It eliminates the electricity bill entirely, not reduces it, eliminates it. A wind tower generates revenue for no one. It is made of clay or concrete or sheet metal. It has no compressor to fail, no refrigerant to leak, no filter to replace, no annual maintenance contract, no warranty to expire conveniently after the manufacturer releases a new model. It costs nothing to operate, and it lasts for centuries. The Daulatabad Garden windcatcher is 279 years old. Name one air conditioning unit that will last 20. The average residential central air system lasts between 15 and 20 years before it needs full replacement. The average cost of that replacement is between $5,000 and $12,500. The Badgir needs nothing. It just stands there, working. This is not the first time this technology was suppressed by economics disguised as regulation. In 1946, an Egyptian architect named Hassan Fathy began construction on a village called New Gurna, near Luxor. Fathy was trained in modern architecture at Cairo University, but he had spent years studying the traditional building methods of Upper Egypt, including the malkaf, the Egyptian version of the windcatcher. The malkaf is a single directional wind scoop oriented toward the prevailing wind that channels air down into the interior of the building. Fathy incorporated malkaf towers, mud brick construction, domed roofs, and courtyard ventilation into his design for New Gurna. His technique was precise. He oriented each malkaf toward the prevailing north wind that blows across the Nile Valley. He connected the base of each wind scoop to a mashrabia, a latticed wooden screen that filtered dust and diffused incoming air across the full width of the room. Below the mashrabia, he placed a salsabil, a marble slab with thin channels of running water, so that the incoming breeze passed over the wet surface and arrived in the living space both filtered and cooled. The combination of malkaf, mashrabia, and salsabil created a complete passive air conditioning system using materials that any village craftsman could build and maintain. No imported components, no specialized tools, no ongoing energy costs. The village was meant to house over 7,000 people displaced from their homes near the Valley of the Kings. Every building was designed to be cool without electricity, built from local materials without imported products, and constructed by the villagers themselves without outside contractors. The Egyptian government undermined the project. Construction was sabotaged, funding was cut, and the village was never completed as designed. Fathy spent decades advocating for what he called architecture for the poor, designing buildings that ordinary people could build and cool themselves without dependence on industrial supply chains. His 1973 book of the same name was published by the University of Chicago Press and became one of the most influential architecture texts of the 20th century. But the buildings he designed were largely demolished or abandoned. The malkaf towers he incorporated were torn down. The passive cooling principles he championed were not adopted into Egyptian building codes. Hassan Fathy received the Chairman's Award from the Aga Khan Award for Architecture in 1980. He died in 1989. His ideas are taught in architecture schools around the world. They are built almost nowhere. The New Gurna village he designed near Luxor still partially stands, crumbling, a monument to what could have been. Architecture students visit it like a pilgrimage. Then they go home and design buildings with central air. I personally think Hassan Fathy's story is the most heartbreaking part of this entire subject. He had the science, he had the proof, he had buildings that worked, and he was defeated not by physics, but by the economics of an industry that cannot profit from buildings that cool themselves. Last summer, during the worst heat wave to hit the American Southwest in recorded history, the power grid in Texas came within 4 minutes of a cascading blackout. 4 minutes. Emergency alerts went out to 30 million people, asking them to turn off their air conditioning in 112-degree heat. Hospitals switched to backup generators. Elderly residents were told to go to cooling shelters. The entire electrical infrastructure of the 9th largest economy on Earth nearly collapsed because too many air conditioning compressors turned on at the same time. Meanwhile, in Yazd, 700 towers kept doing what they have done since the Achaemenid Empire. The oldest surviving examples in the city date to the 14th century. Archaeological evidence of the same principles appears in Egyptian tomb paintings from the time of the pharaohs and in Assyrian palace reliefs from the reign of Sargon II around 700 BCE. Nobody in Yazd received an emergency alert. Nobody was asked to stop cooling their home. Nobody's tower tripped a breaker or overloaded a transformer. The wind kept blowing. The air kept moving. The buildings stayed cool. If you are watching this and thinking that there must be a catch, that there must be some technical reason why this cannot work in the United States, I want you to consider one thing. The catch is not technical. A federally funded building in the Utah desert has proven it works for 26 years. A British company sells code-compliant versions right now. Researchers have published the computational fluid dynamics to back it up. The catch is that a $299 billion industry writes the codes, funds the standards committees, and trains the inspectors, and a tower made of clay does not need any of them. Subscribe if you want to keep seeing these stories, because there is a reason they do not show up in your feed on their own.